So next we do one example on how we do the DC analysis for direct coupled multi-stage amplifier. Okay, so this is a multi-stage amplifier consists of two BJTs. So the first stage is common. This is common emitter. This is with bypass, and then the second stage is common collector. Okay. So the question is we want to determine the Q point for the Q1. Q1 is transistor 1 and Q2 is transistor 2. So the Q point is the collector current and the VCE voltage. So the Q point is we want to calculate the ICQ1, ICQ2, Vce1 and Vce2. So where is the ICQ1? ICQ1 is the current at the collector. This is the ICQ1. This is the ICQ2. Vce1 is the collector emitter voltage at the first transistor, and this is the Vce2. Okay. When you want to do the DC analysis, you need to remove the capacitor. So at DC operation, the capacitor behave as the open circuit. So you need to remove this part, and you need to remove this part, as well as the load part. Okay. So and then you examine whether you have the voltage divider circuit. So yes, you have the voltage divider circuit in the first stage. So you need to simplify the circuit. So how you simplify the circuit? So by calculating the Thevenin resistance and the voltage Thevenin. Okay, the R Thevenin here is equal to R1 parallel with R2. Okay, so R1 is equal to 33K, R2 is 10K. Okay, so this is you will get 7.67 kilo ohm. Okay, for the V Thevenin, so it's not R Thevenin. For the V Thevenin, so V Thevenin is the voltage division between the R2 and R1. So this is a voltage drop at the R2. So this is the V Thevenin is equal to 10K over 10K plus 33K times 14. So this is equal to 3.26 volt. Okay. So when you have calculated this one, you can redraw the circuit. So the circuit will looks like this. So this is your RC here. This is your RE1, so R Thevenin, and you have your V Thevenin. So this is the V Thevenin, R Thevenin. Connection to the second transistor. This is R2, RE2, and yeah, this is connected directly to the VCC. Okay. So this is the simplified circuit. So you can start calculating the ICQ1 and ICQ2. So how we can solve the Q point? So we will do the KVL. First we will do the KVL at input Q1. So input Q1, we do the KVL here. Okay, this is the first KVL. So from this KVL, you will get the IB1, the base current at the Q1, and then you can get the ICQ1. ICQ1 is here. This is the ICQ1. Okay. So we do the KVL. So Vthevenin is 3.26 plus voltage drop at the Rthevenin. The current at the Rthevenin is base current B1, IB1, times the Rthevenin is 7.67K. And then between base and emitter, don't forget to put the voltage drop 0.7. And then this one is the current at the RE1 is emitter current. This is equal to beta 1 plus 1. So beta 1 is 100. So this is 100 plus 1 IB1. RE1 is 2.2K equal to 0. So this calculation will give you the IB1 equal to 11.17 microampere. Okay. From the IB1 value, can calculate the ICQ1 value equal to beta IB. So this is 100 times 11.17 micro. So this is 1.12 milliampere. Okay, when you have calculated the ICQ1, so next we calculate the ICQ2. Okay, so what we do is we do the KVL at input Q2. So our objective is you want to solve the IB2, and then when we solve the IB2, we can get the ICQ2. Okay, so where is the KVL loop? The KVL loop that we going to analyze is this KVL loop. Okay, take note that the current at the RC, this RC, is not exactly equal to ICQ1, because we have here, this is the, because we have the base current for the second transistor. So this is the IB2. So the current at the RC is ICQ1. So the current here is ICQ1 plus IB2. So this is the current here. So the KVL will looks like you can calculate the KVL. You can write down the KVL as the VCC is 14. So this is minus 14 plus voltage drop at the RC. So RC is 6.8K. The current is ICQ1 plus IB2. ICQ1, we know the ICQ1 is 1.12 milli, plus this is IB2 is unknown, and RC is 6.8K, and then plus the voltage drop at the VE. So this is 0.7 plus the voltage drop at RE2 is beta 2 plus 1. Beta 2 is 50 plus 1 times IB2. RE2 is 1.2K. This is equal to 0. Okay. From this KVL, you can solve the IB because this solution only has the IB. So this is the IB2 is equal to 83.6 So since you know the IBQ, you can calculate the ICQ2 beta IB. So beta is 50 times 83.6 micro. So this is equal to 4.18 milliampere. So we have calculated the ICQ1 and ICQ2. So next, how we calculate the Vce1 and Vce2. So we start with the Vce2 because this is much easier. Okay, we know right now this is the 1.12 milli, and this is the IB2. IB2 is 83.6 micro, and this is the ICQ is 4.18 milli. Okay. So the VCEQ from the KVL at the collector emitter of Q1, Q2, at the Q2. So this is the KVL here. So the KVL start from VCC. This is minus 14 plus. There's no RC here, so no voltage drop. So we have the VCE2. The voltage here, this is the VCE2 and plus the voltage drop at the RE2. Voltage drop at the RE2 is beta 2 plus 1 times IB2. So this is 50 plus 1, 83.6 micro, and then times the 1.2K equal to 0. So this will give you the VCE2 equal to 14 minus 5.12 equal to 8.88 volt. So this is your VCE2. Okay, for the VCE1, you can do the same. You can write down the KVL at the collector emitter loop. So this loop. So KVL at collector emitter Q1. So KVL start from the VCC. So this is minus 14 plus voltage drop at the RC. So voltage drop at the RC, the current is 1.12 milli plus 83.6 microampere. So this is 1.12 milli plus micro, convert to the milli. So this is 0.0836 milli times the resistor is 6.8K. And then you have the VCE1 plus the voltage drop at the RE2. RE1 is beta plus 1 times IB1. So IB1 is 11.17 micro. So this is 11.17 micro times 2.2K. So this is equal to 0. So VCE1 equal to 14 minus 8.18 minus this part is 2.48. So the answer is 3.34 volt. Okay, so now you have finished calculated the Q point for both transistor Q1 and Q2. So the ICQ1 equal to 1.12 milliampere, VCE1 is equal to 3.34 volt, ICQ2 is 4.18 milli, and VCE2 is equal to 8.88 volt.